Good morning everybody and welcome again to our course on Introduction to Mechanical Micromachining. In the last class we were discussing about the burr formation and we have seen that depending on the material properties and depending on the different parameter settings we will encounter different type of burrs. So, this is what we have seen in the last slide and we have seen that there are two different ways by which burrs will be formed depending on the material properties. On the top row it is a ductile material burr formation and the bottom part it is a burr formation in the brittle material. Only difference happens in the last slide where you can see that this is written positive burrs and here it is written negative burrs. Why it is so? Because we have seen that this is the what is the workpiece surface we required. That should be, that means there should not be any type of additional material available or there should not be any type of additional material removed. So, if this is our required geometry, then this is the something extra which is attached with the workpiece surface. So, that is why it is called the positive burrs. But if you see this brittle material, at that time you can see that this is what is required, but in this case this is the additional material or the required material which is removed with the surface. So, that is why it is called negative burr, because something is missing from here, and that we have seen in the last class. Apart from the material properties, if you set a different process parameter like a speed feed and depth of cut, speed feed and depth of cut, at that time also you can control the burr formation. Even you machine a ductile material with a different particular speed, feed and depth of cut, you will encounter different type of positive burrs, that means smaller size, bigger size, and sometimes it will be very low also. So, we have to play with this process parameter as well as the material property, so that we can get the minimum burr formation on the final machine component. So, let us continue our discussion further on this topic. Now, coming to the burr formation in the up milling and the down milling process. Now, we have seen that let us see that what is the up milling and down milling first. Now, consider that this is your cutter and this is your workpiece and this is rotating in this direction and your workpiece is also moving in this direction. Right now, we are talking about the horizontal milling machine. Right, because in horizontal milling machine your tool or is in shape of a rotated disc type of cutter and it is mounted on a horizontal arbor. Now, if this is the case, then what is going to happen, that your workpiece when it is moving from left side to the right side, at that time your tool will rotate in the anti-clockwise direction and you can get the material removal rate. So, this particular thing is one and this is the another thing. Let me clear it first. So, again let us not change the direction of the cutter, but let us change the direction of the workpiece feed. So, this is the another diagram. Now, this is you consider this cutter is going down and then this is called the down milling, and when this is cutter is rotating in anti-clockwise direction, but your workpiece is moving from right to left side, at that time this is called up milling. Right. So, in this case if you consider this part, now how you can name this thing down milling, because your cutter is moving in the downward direction with respect to the top surface of the workpiece. Now, this is the top surface and this is the machine surface by means of this milling cutter, and in this particular case you can consider with respect to this top surface your cutter is moving upside in this direction, that is why it is called the up milling process. This is we are discussing or we are giving some name in terms of the movement of the workpiece with respect to the rotation of the cutting tool. Now, you can see the on the side of the up milling cutting, the cutting direction is parallel to the feed direction. So, let us see, this is also one of the ways by which we can define in terms of the feed direction. Now, you can see here in this case the cutter tool is rotating in this direction and tool is given feed direction in this direction. Mostly in right now it is showing that the tool is giving feed, but in this particular in machining operation mostly what happens that your tool is stationary in the xy plane, but your workpiece is actually moving in the this direction, right. So, this particular diagram what we are showing here, it is on the vertical milling machine. Right, and whatever we are explained in this particular diagram, this was about the horizontal milling machine, because in the horizontal milling machine we encountered these two different type of up milling and down milling in a different configuration, because you have to change the direction of either the workpiece or the cutting tool, so that you can get the up milling or the down milling. But if you talk about the vertical milling machine, you will encounter both the things in a same process if you are doing machining of a slot cutting. So, now here this is called the slot cutting. So, this is the width of the slot and depth depending on the parameter settings. Right now it is actually the across this particular page. So, now if you see this particular diagram, here it is written up milling and here it is written down milling. That means, both the things will encounter in a single machining operation. Why it is called up milling? Now, let us see this particular diagram with this one. Now, you can see that your workpiece is moving in this direction and your tool is rotating in this direction. So, both the directions are opposite to each other, and that is following this particular trend. Your workpiece is your tool cutting tool is moving in the anti-clockwise direction and the workpiece is moving from right to the left direction. So, if you see this particular zone in this direction, you can understand that your tool is rotating in this direction. Let us draw it here. So, your tool is rotating in this direction. So, your this is your cutting tool, right, and this is your workpiece. Right. So, this one is now moving in this direction, and this cutter is moving in this direction. Now, this is equivalent to this particular diagram, and now consider this particular size at this location. This is actually equivalent to this one. Why it is like that? Because now if you see in this direction, the tool is moving in this direction, right. So, tool, let us consider it is again moving in this direction. So, there will not be any change in the direction of the rotation, but if you see your workpiece is also moving in the same direction, right, because your this is the workpiece direction, this is the tool rotation. So, this particular thing is equivalent to the down milling process, right. So, this is how you can define in terms of the movement of the workpiece or in terms of the feed to the cutting tool. So, on the side of the milling cutting, the cutting direction is parallel to the feed direction, and on the side of the down milling, in this particular case, the cutting direction is opposite to the feed direction. So, this is the feed direction, your cutting direction is this direction right now in this direction. So, it is opposite to each other, but it is very convenient to use this particular diagram to understand the up milling and down milling in place of feed direction, because this is more clear to understand in terms of the workpiece movement rather than in terms of the feed movement. Right. So, here what is the important thing? The burr formation limits on the minimum wall size that could be machined. So, let us see that example, that what is the problem with respect to the minimum wall size. Now, consider that this is our workpiece. Now, we are talking all about the vertical milling machine operation only, and our cutting tool is at this location. Okay, and we want to do some type of machining operation like this. Let us see that we want to cut like whatever is this diameter, this diameter, let us consider it is a 500 micron, right. So, we are not going to increase the size of or width of the channel, but we will keep same as it is. So, you do not need to travel your tool more than one times in the same direction. So, let us consider the width of the channel is same as the 5 micron. Okay. And after that our objective is the let us get the different type of wall size. So, this is the wall size, and again there is a 500 micron, and then after that let us reduce the size of the wall. So, this is the second size of the wall, and then again it is a 500 micron, and something it is even smaller than that. And again there is a 500 micron. So, this is our objective, how we want to make this particular and all this width are 500 micron, but difference is here. So, these are the differences. Okay. Here it is considered this width is a W1, W2 and W3. So, W1 is bigger than W2 and W2 is bigger than W3. Now, we want to see that up to which location or up to which dimension we can reduce the width of this particular wall. Now, consider we will start with the fresh workpiece. In the fresh workpiece, what is the advantage that let us start machining from at this location. So, your cutting tool is cutting something like this in the first go. So, what is the advantage of going with this particular thing, that you have large amount of material available on this side. So, material resistance will be very high, or it will support the cutting tool forces. Now, if you see from the vertical direction, this is your cutting tool, and then cutting tool will be rotating in this direction. This is your rotation direction, and now consider this is your workpiece. Then you will encounter two different type of forces. This is the normal force and this is the tangential force. So, this force is Fn, right, and because of these two different forces you will get material removal rate from the surface. So, now in the first cut you will not most probably encounter any type of problems, but when you go for the next cut. So, this is the next cut. Now, consider we are talking about right now W1. So, here you can see that the width is almost same as the size of the cutting tool. So, at that time also probably you may not encounter so much of forces, but now let us discuss about the last one, that now you have removed some of the materials already from the surface. So, now this is the what is happening in this case. So, these things are removed. Right, and now consider that your cutting tool is here at this location, last one, right. So, when you are cutting the last one, you have already cut one particular wall which is here, right. So, you are cutting your last wall here at this, let us discuss on this only. So, this is your cutting tool. And you are cutting this last channel, so that you will get the width of this wall. This is the wall thickness, right. So, when you are cutting the last channel or the channel just beside, you will get a very thin wall. At that time what is going to happen in this case, the material resistance or the support of this material will be very low in this case. Right. So, this is the last one. So, material support less. So, because of that reason what is going to happen, either this particular last wall, let me draw it here, this is your last wall and this is your cutter width and there will be some other surface available here, right. So, your cutting tool is already inserted inside it and it is rotating. So, when it is moving at that time what is going to happen, you will encounter this FT and FN, right. So, this will be the FN and FT will be, if you see from the top, this will be your FT, right. So, because of this FN, when FN is moving in the, or it is exerting on this surface, this particular thickness of the wall is very less. So, it will actually bend. So, you may get this kind of things, bending of this particular last wall, or where the wall thickness is very less, at that time you will encounter bending. So, because of the bending what is going to happen, that you are not able to cut the width of this channel appropriately, because earlier suppose that your requirement is, consider this was 500 micron, let us consider it is 100 micron is the wall thickness which you want to cut at the last one. But because of this bending what is going to happen, it will be little bit bigger than this one. Bigger than 100 micron, because it will bend. So, some extra material will be here and you are not able to cut this material very easily. So, bending is the one problem, and because of this bending you are able to get, or you are not able to get this particular 100 micron thickness of the wall, and you will get something else which is not you required. So, this is the problem, that wherever the size of the wall is very less, at that time the material resistance will be very less. Because of that, the force is encountered by or exerted by this milling cutter here, that cutter will exert more force, and that force, because of that force your particular wall will be bent, and then you will get the different size of the wall thickness. So, there is a problem with this thing. So, if you want to cut any channel with a some thickness, at that time you have to understand what is the size of the milling cutter you are using and what is the minimum size you can cut without bending this particular wall, which has a very low wall thickness, right. And now the burr formation again in this case, now you can see, so this is the machine channel by a vertical milling cutter, and you can consider this is moving in this direction. Now, this is the cutter movement. So, let us draw cutter here. So, this is the cutter and it is going in this direction. So, if it is going in this direction, you can consider that this is called the one region and this is called another region, and these are the top burr formation and this is the bottom burr formation. Now, consider this phenomena, you consider this, this is the feed direction, right. So, this is the feed direction. So, our feed direction is shown by this diagram. So, this is our feed direction. Our tool rotation is in anti-clockwise direction, but here it is showing in the clockwise direction. So, the direction, or that means the location of the up milling and down milling will be different here as well as at this location. So, now you can see that up milling has the smaller burrs than the down milling. Now, consider, now this is you can see that this particular size you will find very less burr formation, but in this particular case you will find lot of burr formation. So, this particular size is the up milling. So, this is called the up milling side and this one is called the down milling side. Now, because why it is so in this case, because our feed directions are same, but the tool rotations are different. In this thing it is rotating in this anti-clockwise direction, but in this case it is rotation in the clockwise direction. So, top burr up milling is on this particular side, but in this case up milling is in this side, because of that diagram what we have seen earlier case, that the direction of the workpiece movement and the direction of the cutting tool should be opposite to each other, then you will get the up milling in this case. So, now why this is so? Because it is showing that up milling has the smaller burr formation than the down milling. So, now let us see that also. Now, for that what we have to understand? We have to understand the how tool is approaching the workpiece. Now, this is the case. Now, this is our cutting tool and this is the edge. Now, you consider that your tool is moving in this direction. So, your whatever is the material available here. So, this is the material available. Right. This is the material, your cutter is slowly going from the right side to the left side and it is removing the material. Now, consider that you have some burr formation here at the down up milling side here in this location, right. So, when you have some burr formation, what is going to happen? When your one cutting edge is removing the material, it is generating some burrs. So, wherever this burr formation available here, the next cutting tool or cutting edge, when it is coming into contact with this part, at that time it will remove that burr formation or whatever the burrs are formed here, that will be removed very easily in this case, because your cutting edge or cutting fluid, whatever we are telling here, that will be actually entering into the surface. And when you see at this particular location, at that time what is going to happen here? Your tool is leaving the surface, and in this particular case your tool is entering into the surface. So, by chance if some burrs are formed at this location, there is no way that your cutting tool or the cutting edge will remove that burr formation, because your movement is in this direction. But in this particular side, on the up milling side, if the burrs are formed here, your next cutting edge will remove that burrs very easily and you will get very less burr formation on the up milling side compared to the down milling side, because in the down milling side you will not get the chance to remove that burr formation unless you move this cutting tool again in this direction. Then your up milling becomes down milling and down milling becomes up milling without changing the rotation of the cutting tool. So, at that time you will get a chance to remove this burr formation from here. So, this is one of the strategies by which you can reduce the burr formation, that in the if you want to cut a one channel, then you cut the channel in this direction and this is your cutting tool direction. Now, after that we know that if it is rotating in this direction, let us take the same example here. Let us not change the rotation direction. Now, see, this is the direction. So, let us see it is moving in this direction, right, moving in this direction, going in this direction. So, that is the reason that you will get more burr formation here and less burr formation on this side. So, after cutting or after reaching here, then what we have to do, that let us change the movement of the direction without changing the RPM, that are not RPM, but the rotation direction of the cutting tool. We are changing the feed direction only. So, when you move in this direction, then you will get the more burr formation on this side. But we know that this is already machined on the up milling side. So, you will not get more burr formation here, because there is already burrs are removed and this channel is already cut. So, movement of this thing in this direction, it is objective of this thing is only to remove the burr formation here, not to do cutting, because cutting is already done in the one or the first cycle, and next cycle our objective is to remove the burr which are formed on the down milling side. So, when this is going to happen, at that time it will remove this burrs and then you will get the less burr formation. The only thing that your operation time will be double, because you are doing cutting in the one direction, that is effective cutting. In the next same direction on the same channel, you are doing the burr removal only, and not burr actually removal, but reducing the burr formation. So, that is what is happening in this case. And there are other strategies also. We will discuss these things as we go ahead in this course, right. So, up milling side, the burrs is a poison burr formed only by side bulging action. So, we have already seen that what are the poison burrs. So, this is the poison burr, and on the down milling side, top burr is formed by the action of the chip material tearing away as it flows, as well as the side bulging deformation. So, let us see first one, this thing up milling side. Now, we have seen in this diagram that if you see this particular thing, that there is a rod which is rotating in this direction, and then we are pressing this rod into the material. This is the feed direction, right. So, your rotation will be, that means your material will be moved in this direction to this direction, right, because rotation direction is this one. So, when your material is displaced from here to here, you will get that wherever the material is displaced, it will be accumulated at this location. So, that is called the entrance bar at this location, and this is the representing the cylinder representing the cutting tool. So, that is same thing happening here in this particular case. So, here what is going to happen, that whatever material is removed from here from this location, that will be accumulated onto this particular side, and that is because of that reason you are end up with some type of poison burst. And if you see the down milling, in this particular case the top burst is formed by the action of the chip material tearing away as it flows, as well as the side bulging operation. So, in this particular case what we are going to do, that when it is rotating in this direction, at that time this material is teared away from the air, but your cutting edge will not be able to remove the teared material, that means it will stay there only, and because of that only the side bulging happens in this case, and then chip material will be flowed on the top surface. So, that is the reason that you are end up with the different type of bursts on the down milling and some other type of bursts on the up milling side. Now, coming to material properties. Now, if you see, the material properties are also playing important, that we have already seen in the last class, that if the material is ductile, then what is going to happen, high elastic plastic deformation in the machining, and that is the reason that larger and more bursts are likely to form. So, that is because of the material property, that material is able to elongate little bit more, and by that time your tool will be passed from the surface and you are not able to remove it effectively. And if you see the hard material you will get the less burst, because it will be exactly opposite to this part. But again there is a problem in the hard material also, because if you machine a hard material, your tool wear will be also very high, and when the tool wear is high, we have seen already that what is the effect of cutting edge radius, because it should be very, very sharp, and if the sharpness is gone, that means by means of wear, then what is going to happen, that negative rake angle, plowing, and this all these things starts coming into action, and again you will get the more burr formation. So, from this slide we can understand that whether you cut a ductile material or the hard material, you cannot avoid the burr formation. Only thing we have to see that by changing the different parameter setting, how we can reduce the burr formation, but by this we can understand that there is no way you can eliminate completely the burr formation. Now, let us see about the burr formation strategies. In this case, let us see that if you understand from the earlier slide that if your depth of cut is small, there is a chance that you will understand that you will get the less height in the burr. But that is mostly not true here, because we know that by changing the depth of cut, what we are going to do, that we are getting some type of rubbing and plowing mechanism, because again we have to scale this depth of cut with respect to the cutting edge radius. If the depth of cut is so small that your cutting edge radius becomes more, then you are end up with the rubbing and the plowing mechanism, and then you will get the formation of the large and the strong burst. That is not the advisable in this case. So, going with a small depth of cut and to get the high less burr height formation, that will not be true in all the cases, but that again depends on the material properties. Now, there is another way, that is why let us increase the number of fluids. Now, in the earlier slide what we have seen, that this is considered, this is the 4 fluid cutter and this is the 2 fluid cutter, that means the number of fluids. So, in this location 4 fluids or the 4 edges will remove the material, and in this case is only the 2 edges will remove the material, right. So, what is going to happen in this case, that if you increase the number of fluids, that means the 4 fluids, at that time less chip load, that means if you can't give a same feed rate, you are not changing the feed rate, then the material whichever is removed, that will be shared by the 4 number of fluids, and in this case it will be shared by the 2 fluids. So, per fluid you will get more material removal in this case per fluid will be less, because 4 fluids are coming into action, right. So, less chip load will be there in this case, and in this case its chip load will be high, that is by feed per tooth per revolution, and that is the reason you may get the less uncut chip thickness and you will get the less burr formation. But again it depends on the other parameters, that what is the feed rate, RPM, whether there is a coating or not, many things will play important role. So, whatever we are writing here and what we are discussing, this cannot be a generalized statement, right, because if you apply this particular thing, that by logically we can understand that less formation height is possible if your depth of cut is less, but there are other parameters also playing important role, that it will change the definition of these things. So, let us not generalize this statement, but we will see that material to material and depending on the parameter setting, these things can be taken up very easily, right. And the high cutting velocity lead to the less burr formation in the micro milling of the steel. Now, what is the advantage that if you increase the cutting velocity mostly, that means if your cutting tool diameter is same, then basically you are increasing the RPM, because in the machining operation basically RPM is very fuzzy term, because you have to also see the what is the diameter of the cutting tool which you are using. That means the cutting velocity is very important, millimeter per minute or the millimeter per second in place of the revolution per revolution per minute, something like that. So, in this particular case, this is observed in the machining of the steel, that if you increase the cutting velocity, you will encounter less burr formation. Another thing, the coated tool reduce the burr formation in the micro milling of the hardened steel, because we know that when you want to do machining of a hard material, at that time you have to make sure that your cutting edge should be very sharp, cutting edge sharpness, right. This is important, because you have to play with this parameter, you have to make sure that this sharpness you are retaining for a longer period of time. That is possible by coating the cutting tool. So, if you do coating on the cutting tool, what is going to happen? The coating is very hard, and when this is the cutting tool and this is the coating on the top, obviously you will get little bit of rounding of the edge because of the coating, but that is still within the limit of the uncut cutting edge radius features, whatever we want to fabricate. So, by coating the cutting tool, we are saving or we are protecting this particular cutting edge from the very high wear. So, that is the reason that when you want to do machining of this hardened steel, at that time better to use a coated tool. Without coated tool, your cutting edge becomes dull very quickly, and then you are going with this particular rubbing and plowing mechanism, and that is not good for the proper machining operation. And the use of cutting fluid, that is also important, because we know that we are actually doing machining by a mechanical method. That means there is a contact between the cutting tool and the workpiece. Friction and heat generation is very high in this particular case. So, that is the reason that we have to find some of the ways by which we can dissipate this heat and we can cool down very easily, so that there will not be any type of more damage because of the friction and the heat temperature. So, in this case mostly we go with a two different ways. By there is the mist cooling and another is the flood cooling. Flood cooling is mostly we use in a conventional machining, and this mostly we go with a micro machining, because there are reasons. Because in flood cooling, what is the happen, that the amount of coolant which you are using, it is extremely high, and many times what happen, the diameter of the cutting tool is also very low in the micro machining, and because of that sometimes you may get some type of problem with if you use with a flood cooling. Mist cooling, it is something like that, you are using very fine mixture of the fluid, that is coolant as well as the air, so that you are end up with a some type of very fine mist out of the coolant and the air mixture, and that is very easy to modulate or easy to focus on some location. Because we know that in micro machining the size of the chip is very small. So, you do not need to flood away the very high amount of chips, but in the conventional machining what we know that the size of the chip is very large, and you have to make sure that the chips are not actually accommodating the machining zone. So, it should be thrown away without any problem. So, in the mist cooling is very preferable in case of micro machining operation, and the flood cooling mostly people use with the conventional machining, but still people have started working of the using mist coolant for the conventional machining also. So, let me stop this class here in this and we will continue this burr formation and different type of strategies by which we can reduce the burrs in the next class. Thank you very much.